Hello class, and welcome to our next section here, the last one for Unit 4 on Section 4.6, Impulses and Delta Functions. So an impulse, a force f of t that acts in the interval from a to b, the course interval from a to b, and has a zero outside of it. And is, the value of that function is zero outside of that interval. Examples include hitting a baseball with a bat and a lightning bolt. The principal effect of the force depends on the impulse p being equal to the integral from a to b of f of t dt. By Newton's law, f of t is equal to m times v prime of t. That would be the derivative with respect to t, first derivative with respect to t of m times v of t, which yields p is equal to the integral from a to b of that first derivative with respect to t of m times v of t dt, which will just give us m times v of b minus m times v of a. So the unit impulse, denoted by d sub a comma epsilon, is 1 over epsilon for values of t being between a, including a, and up to a plus epsilon. Otherwise, it's 0. And this integrates to be the value of 1, as we can see in this graph in the upper right-hand corner. We have that from interval here from a to a plus epsilon, so we have that difference of epsilon here. You can see it makes, based on this region we have graphed, it gives us an area here of 1, as we have epsilon times 1 over epsilon. So it gives that area of 1. So p would be the integral from a to b of this unit impulse function. Dt is equal to the integral from a to a plus epsilon of 1 over epsilon dt, which is equal to 1. Same thing if this is from 0 to infinity as well. We want to find the instantaneous impulse being delta sub a of t is equal to the limit as epsilon approaches 0 of that unit impulse, where a is greater than or equal to 0. So we get that delta sub a of t to be positive infinity when t is a, or 0 when it's not a. And this is the Dirac delta function, named after the theoretical physicist P.A.M. Dirac, born in 1902, died in 1984. So this delta function is basically an operator, just like the Laplace transform. We could take the definition of delta sub a of t to be the integral from 0 to infinity of g of t times delta sub a of t dt. And that would be equal to some net value g of a, to denote the operation, with g of t as some continuous function. The Laplace transform of this delta function would be the Laplace transform of delta sub a of t is equal to e to the negative as with a greater than or equal to 0. And if we let delta of t be equal to delta sub 0 of t, and delta of t minus a to be equal to delta sub a of t, with a being 0, then the Laplace transform of delta of t would just be the value of 1. And this picture here on the bottom just denotes we put in some function g of t, and we spit out that definition there of delta for that delta function. So the inputs. We let the mechanical system with response x of t have the external force f of t, determined by a times x double prime plus bx prime plus cx is equal to f of t. The response to a unit impulse at t is equal to a is when we replace f of t to be delta sub a of t, to make a times x double prime plus bx prime plus cx is equal to delta sub a of t. Its solution would be x of t is equal to the limit as epsilon approaches 0 of x sub epsilon of t, where x sub epsilon of t is a solution of a times x double prime plus bx prime plus cx is equal to that unit delta function d sub a comma epsilon of t, where that d sub a comma epsilon of t is 1 over epsilon times u sub a of t minus u sub a plus epsilon of t to be some ordinary function. So if we utilize the initial conditions, x of 0 is equal to x prime of 0, with both of those being 0, the Laplace transform of x sub epsilon is a times s squared plus bs plus c times that Laplace transform capital X sub epsilon of s is equal to 1 over epsilon times e to the negative as divided by s minus e to the negative of a plus epsilon times s divided by s. So e to the negative as times 1 minus e to the negative s times epsilon divided by s times epsilon. But the right side of what we just went through here, so this portion, the limit as epsilon approaches 0 of that is just equal to 1 by L'Hopital's rule. So that means a times s squared plus bs plus c times capital X of s is e to the negative as, as long as capital X of s is the limit as epsilon approaches 0 of capital X sub epsilon of little x. So as an example, a mass m is equal to 1 is attached to a spring with constant k is equal to 4. There will be no dash pot. The mass is released from rest with x of 0 is equal to 3. And at the instant t is equal to 2 pi, the mass is struck with a hammer, providing an impulse with p being 8. We want the motion of this mass. So, the initial value problem that we have here is going to be x double prime plus 4x is equal to 8 times delta sub 2 pi of t. And here, x of 0 is 3, and x prime of 0 is 0. Okay, so if we were to apply this Laplace transform, so apply Laplace transform, applying that Laplace transform, we would get s squared times capital X of s minus 3s plus 4 times capital X of s is equal to 8 times e to the negative 2 pi s. So, capital X of s would be equal to 3s divided by s squared plus 4 plus 8 times e to the negative 2 pi s divided by s squared plus 4. So, taking the inverse transform of this, inverse Laplace transform specifically, will produce the function x of t is 3 times the cosine of 2t plus 4 times u of t minus 2 pi times the sine of 2 times t minus 2 pi So we can simplify that a bit to be 3 times the cosine of 2t plus 4 times u sub 2 pi of t times the sine of 2t. Okay, so from this, 3 times the cosine of 2t plus 4 times the sine of 2t is equal to 5 times the cosine of 2t minus alpha, with alpha being the inverse tangent of 4/3. And that number is about 0.9273. So, because of this, we can rewrite our position function x of t with our two cases. So, 3 times the cosine of 2t. This is when t is less than 2 pi. And the other one being 5 times the cosine of 2t minus 0.9273. And this is when t is greater than or equal to 2 pi. So when t is equal to 2 pi, we have a discontinuity in the velocity. So discontinuity in velocity. So the formal definition of the derivative of this unit step function, despite not being differentiable in the ordinary sense, is the first derivative with respect to t of u sub a of t is delta sub a of t, which is delta of t minus a. So here's another example. We want to let the RLC circuit have a resistor of 110 ohms, L being 1 Henry, and C being 0.001 farads, and a battery is supplying E sub 0 is equal to 90 volts. We want to suppose the circuit is initially passive with no current and no charge. At time t is equal to 0, the switch is closed, and at time t is equal to 1, it's opened and left open. We want the resulting current I of t in the circuit. So typically this equation is L times that second derivative of I plus R times I prime plus 1 over C times I is equal to E prime of t. So E of t in this case is 90 minus 90 times u of t minus 1. So 90 minus 90 u sub 1 of t. So the derivative of E, first derivative of E, is negative 90 times delta of t minus 1. So the initial value problem for this is going to be I double prime plus 110 times I prime plus 1000 I. That's going to be equal to negative 90 times delta of t minus 1. This is with I of 0 to be 0, and I prime of 0 is equal to 90. So if we use this Laplace transform, we will get, I'll put it here on the right hand side, the Laplace transform, this will give us s squared times I of s minus 90 plus 110 times s times I of s plus 1000 times I of s. And this would be equal to negative 90 times e to the negative s. So from this, I of s would just be equal to this function here. 90 times 1 minus e to the negative s divided by s squared plus 110s plus 1000. For example number 3, we have consider a mass on a spring with m is equal to k, which is equal to 1, x of 0 and x prime of 0 being 0, and each of the instance of t being 0, pi, 2 pi, 3 pi, n pi. The mass is struck with a hammer blow with a unit impulse, and we want to determine the resulting motion, which you can see kind of in the graph I have there on the top. But for this, the initial value problem we are trying to solve is going to be x double prime plus x is equal to the sum from n is 0 to infinity of delta sub n pi of t, where x of 0 and x prime of 0 are both 0. Alright, so we know that the Laplace transform of delta sub n pi of t would be equal to e to the negative n pi times x. So, applying that Laplace transform, we would get s squared times capital X of s plus capital X of s is equal to the sum from n is 0 to infinity of e to the negative n pi s. So solving for x of s, capital X of s, this would be the sum from n is 0 to infinity of e to the negative n pi s divided by s squared plus 1 from what we have in our function. So applying that inverse Laplace transform, let me write that here on the side, we would get x of t is equal to the sum from n is 0 to infinity of u of t minus n times pi times the sine of t minus n pi. We do know that the sine of t minus n pi is the same thing as negative 1 to the nth power times the sine of t. And that u of t minus n pi is equal to 0 when t is less than n pi. So, as long as t is between n pi and n plus 1 times pi, we could write our function to be x of t is equal to the sine of t minus the sine of t plus the sine of t. And this keeps going, alternating the sine, all the way up to negative 1 to the nth power times the sine of t. So, because of this, x of t is equal to the sine of t when n is even, or 0 when n is odd, which would then produce that graph I have here in the upper right hand corner. So, a couple special parts here. If we consider a physical system in which the output response x of t to the input function f of t is described as a times x double prime plus bx prime plus cx is equal to f of t, the solution, capital X of s, is capital F of s divided by a times s squared plus bs plus c is equal to capital W of s times capital F of s. W of s is our transfer function, is equal to 1 over a times s squared plus bs plus c. The weight function w of t is the Laplace transform of that transfer function. And the convolution x of t is equal to the integral from 0 to t of w of tau times f of t minus tau d tau is Duhamel's principle. Alright, so example number 4. I want to apply Duhamel's principle to the mass spring dashpot system. X double prime plus 6x prime plus 10x is equal to f of t with external force f of t. So capital W of s would be 1 over, based on this would be s squared plus 6s plus 10. So we can factor that. 1 divided by, completing the square, this would give us s plus 3 squared. And we have 1 left over, so plus 1. And from that, this is our transfer function. The weight function would be little w of t is e to the negative 3t times the sine of t. So Duhamel's principle and let me just fix that L in Duhamel. So Duhamel's principle, this will imply the response x of t to the force f of t And we could see that that would be x of t would be equal to the integral from 0 to t of e to the negative 3 tau times the sine of tau times f of t minus tau d tau. Let me know if you have any questions or concerns. Thank you.